Yeah, thank you for the opportunity to present my study. So I forgot to put my affiliation on my title slide, but I'm at Johns Hopkins. I'm assistant professor of biostatistics. So as you know, the Odyssey has an extensive network of databases that has been mapped to the OMOP common data model. And this is a major strength of Odyssey. On the other hand, the data from individual health systems have made relatively minor contribution to the Odyssey studies in generating treatment effect estimate, because these individual health system databases are often too small to be analyzed individually, but also too heterogeneous to be simply combined and analyzed jointly. And if you're a good statistician, you should be wondering, perhaps we can do something like Bayesian hierarchical modeling to borrow information across these heterogeneous databases. And in terms of the actual statistical model we need, one of the key components of the statistical engine behind Odyssey studies is large-scale L1 penalized regression. In particular, the Odyssey's approach to causal inference relies on what we call large-scale propensity score method, involving tens of thousands of clinical covariates and up close to 1 million patients typically. And currently this is done using the standardized frequencies framework using the Cyclops package developed by Mark Suchard. And this L1 penalized regression critical in the Odyssey studies have a natural Bayesian analog. And so under the Bayesian framework, the inference on the unknown regression coefficient is based on the so-called posterior distribution, which we obtain by multiplying the prior distribution on the regression coefficient with a likelihood function for the data. And the role of the penalty function in the penalized regression is analogous to the role of the prior in the Bayesian framework. In fact, the lasso, the L1 penalized regression, can be interpreted as a Bayesian procedure based on the double exponential prior. And in fact, under the Bayesian framework, the convexity of the objective function is not so important. So we can actually use even better priors like Bayesian bridge prior, which I will be using. Now, one of the main challenges in Bayesian method in practice is that the posterior distributions are analytically intractable. So we Bayesians often rely on Monte Carlo simulations to draw random variable from the posterior distribution and use that to quantify the posterior. And this Monte Carlo simulation can be prohibitively expensive. And in fact, some people dismiss Bayesian method as being impractical in the large scale applications for this reason. But the fact that they don't know how to scale Bayesian method doesn't mean that it doesn't scale. So when I was doing postdoc at UCLA, I, with the financial support from Mark Suchard, came up with a way to scale Bayesian sparse regression to the typical size of the modern observational healthcare data. And I demonstrated its scalability using the Odyssey's replication of the FDA study on comparing dabigatran and warfarin for treating patients with atrial fibrillation. So using IBM MarketScan Medicare database, this study consists of about 70,000 patients and 20,000 clinical covariates. And with a previous state-of-the-art approach for fitting Bayesian sparse regression, fitting the models and getting the treatment effect estimate would have taken almost 2 weeks. And with a new algorithm I came up with, it takes less than a day to fit the whole model. And turns out this new algorithm is also amenable to parallelization using GPU. And I had my PhD student, Andrew Chin, work on adding the GPU support to my Python package. And now whole thing runs in a bit over an hour. And this is in fact faster than Cyclops using CPU. So Cyclops can also use GPU. And this Bayesian sparse regression machinery for Odyssey studies is available through the Python package bayesbridger I have been developing. And I realize many of you are more of an R user than Python user. And if so, you can take advantage of the tool using the bayesbridger package, which is a R wrapper based on reticulate. So thank you very much for your attention.